Now we will find out the peak value, which is nothing but t squared by 4 for this curve. So we are going to find out the value of this peak, which is nothing but t squared by 4. We know the expression. So in the y-axis, the expression is like this: sin squared omega ml t by 2 divided by omega ml squared. So this occurs only when omega ml tends to 0, omega ml equal to 0. So we will keep omega ml equal to x. So when omega ml tends to 0, we are going to substitute this expression and we are going to substitute omega ml equals x. Okay. So when omega ml x, the expression becomes exactly like this. And we have 1 by x squared. We just expand sin x in terms of series exactly like this. So sin x equals x minus x cube by 3 factorial plus x to the power by 5 factorial. Just substitute here. So now we are going to neglect the higher terms. When we are going to neglect the higher terms, we will have only this term alone. So we have 1 by x squared, xt by 2 whole squared. Okay, this squared is there. So that's why this square is there. So we have x squared and x squared will cancel. You have t squared by 4. So the highest order is nothing but, neglecting the highest order, we will have only t squared by 4, which is nothing but the peak value. Okay, so this is the highest value as shown in the figure. Okay, highest value. So as I said, this is very important, 1 mark question. Now we will find out where it becomes 0. The curve becomes 0 exactly at 2 pi by t, 4 pi by t on either side. So where it becomes 0, we will find out. That is when sin n pi equal to 0 for on either side. So we know already this. So sin squared xt by 2 by x squared will be 0 when it is equal to n pi. So this is equal to 0. So xt by 2 equal to plus or minus n pi. So we have x equals plus or minus 2n pi divided by 2. It implies that the transition probability, which is equal to 0, the transition probability in the curve, which is equal to 0 on these values on either side. Okay, when omega ml equal to plus or minus 2 pi by t, plus or minus 4 pi by t, and goes on. So we have omega ml, x equals omega ml, which is equal to plus or minus 2n pi by t, and t can be expressed like this, plus or minus n 2 pi by omega ml. The values are shown in the x-axis in the figure. Okay, these values are shown in the x-axis in the figure. So we can come to know from the figure that this transition probability is an oscillating sinusoidal function. So this is oscillating sinusoidal function. So oscillating sinusoidal function. Only when the peak amplitude decreases slowly, because it has to die out exactly when x tends to infinity, omega ml tends to infinity. So this is oscillating sinusoidal function with a period of 2 pi by omega ml. The transition probability has an interference pattern, as I said. So it has an interference pattern and it is appreciable only when omega ml tends to 0. Omega ml is equal to 0. This is exactly at the centered around, and decays rapidly as omega ml moves away from 0. So it has to die out when moves away from 0. Hence, if the time interval is large, there is appreciable probability. Okay. This means that the transition probability of finding the system EM in a state of energy is greatest only when this condition. We know that omega ml equals EM minus EL divided by h bar, we know already. When omega ml equal to 0, this expression becomes EM L is equal to EL. So this is large when this condition is satisfied. I repeat, this is equal to 0 means EM equals EL. So EM is approximately equal to EL when omega ml is approximately equal to 0. So it implies that, so this effect is large on this condition. EM is almost equal to EL. So it decays rapidly when omega ml moves away from 0. Okay. The height of the main peak increases in proportion to t squared, as we discussed earlier, and the breadth decreases inversely to t. Therefore, the area under the curve is proportional to t. Okay. So this is inversely proportional to t. So as I said, t squared multiplied by 1 by t, that will give us t. Since most of the area is under the central peak, it implies that probability per unit time of the system in the state is proportional to t. It varies linearly with time. Okay, it varies linearly with time. So the transition probability therefore grows linearly with time. the central peak becomes narrower and higher as time increases. This is exactly the property of the delta function. Okay. Okay. Now we will go with problem 1. So this is a related problem, and this problem is very important as far as CSR examination is concerned. A system in an unperturbed state n is suddenly subjected to a constant perturbation h1 of r, which exists during the time 0 to t. Okay, so this is a condition. Find the probability for transition from state L to M and show that it varies simple harmonically with angular frequency is given by this. Okay, and amplitude is given by this. Okay, so now we know already equation 7.28. This is the first order correction for a constant perturbation. We know already this expression, correct? So we know just now we discussed. Okay, this is. Now just integrate this. So when you are going to integrate, this becomes e power I omega ml t divided by I omega ml. This I will cancel and substitute the values, limits. So you will have e power I omega ml t, substituting the lower limit, that will give you 1. So minus 1. Okay. So this term in bracket I can write exactly like this. 1 can be written as e power I omega ml t by t multiplied by e power minus I omega ml t by t. I am going to write this expression as e power I omega ml t separately, e power I omega ml t by 2 multiplied by e power I omega ml t by 2. Is it okay? Here t is here t by 2. Multiply these two will give you e power I omega ml t. You just multiply this, that will give you answer as 1. So this expression in bracket can be written as exactly like this. Okay. Now multiply and divide by 2i. This expression alone. Multiply and divide by 2i. So 2i I have brought it front. So minus 2i divided by h omega ml. The remaining terms let it be like this. This term alone. What is this term? So this is sine. So sine omega ml t by 2. Remaining term let it be like this. So we have the first order connection. So this is your first order connection. So squaring, that will give you the transition probability. Squaring will give you transition probability. Now we are going to square the term. When you are going to square the term, just take a complex conjugate and multiply. So what is a complex conjugate? You are going to change this factor alone. E power I omega ml t by 2 becomes e power minus I omega ml t by 2. So this factor alone. Okay. And of course we have 2i. And this term is there. So complex conjugate will give you plus 2i. So that will give you I into I squared minus 1. Only 1 minus is there, so it will become plus 2 2s are 4. We have 4 divided by h bar squared omega squared ml, and this will become a mod. Okay, constant perturbation will become mod squared, and sine and multiply sine will give you sine squared term. Any doubt? It's a very simple one. So which is the probability for transition from state L to state M? Now we will have to go with the answer. It's given as the angular frequency is given by this and the amplitude is given by this. What is the angular frequency here? Look at the angular frequency. Angular frequency is nothing but omega ml t by 2. So omega ml t by 2, which is equal to Em minus El divided by 2h bar. We know already omega ml equal to this. So by 2 will give you divided by 2, and this will become 2. See, that's why I have written like this. What is the amplitude? This is your amplitude. Correct. 4 divided by h bar squared omega squared ml. Instead of omega squared ml, you can write Em minus El whole square divided by h bar squared. El divided by h bar squared. This h bar squared and this h bar squared will go off. I repeat. So this is your amplitude. I have written instead of omega squared ml, I have written this term here. And this h bar squared and this h bar squared will cancel. We will have only 4. This term together this is an amplitude. This is the phase factor. So this is your amplitude term and this is your phase factor. Look at the problem. See, this is your amplitude. Okay. This is your amplitude which you have obtained. Okay, so now the condition is satisfied. Whatever we want to have, that condition is satisfied. Okay, so this problem is very important problem as far as I said CSL examination is concerned. Okay, so thank you students, we will see in the next class.